Thank you. So I'm going to talk about fundamental lessons that we have learned about string theory. So the first part of my talk is going to be introducing the basic ideas. So string theory, as you may have heard, is a theory which has been being pursued for about 45 years now as a fundamental theory of everything. Now that's a big undertaking. So clearly we cannot achieve everything, even if we limit ourselves just to the fundamental questions, in a complete, detailed form. And that's the case for us today for string theory. We have learned a lot of things about string theory in the past 45 years, but a lot we haven't understood. It is the most promising candidate we have for unifying Einstein's theory of relativity, which is the theory of gravity, with quantum mechanics. So these two particular important pillars of modern physics. And the basic idea in it is that you have to replace basic particles, point particles, elementary particles like quark, by extended objects like strings. That's why it's called string theory. And but these happens at a very, very tiny scales. In other words, from far away distance, this loop might look just like this point. But if you zoom in to about a scale of about 10 to the minus 30 centimeters, then these particles might have some extended features like this string or membrane or some such things. And this is why we call this string theory, the importance of replacing elementary particles by these string-like excitations or string-like configurations. So for example, here is depicted a quark inside the nucleus, which can be viewed as a string if we kind of have a magnifying glass and look at it. And the basic process is for the strings, in terms of producing new strings or interacting, the strings combining, coming along and combining into another string in a very nice form. In this way, you see two strings joining, and the opposite process would have given you a string splitting to two strings. And this underlines all possible interactions that we could, in principle, envision. And in some sense, it's a very nice way to unify all these particles and forces into one object. The particles are unified just to strings and all its vibrational modes. And the interaction is all captured by the simple process of strings coming and joining and forming new strings. But it's too early to present the final formulation of string theory. It's work in progress. And work in progress implies working in this context behind computers, sometimes blackboards. And experiments, unfortunately, can't help, at least not yet. And the problem is that the string, the size of the string is about a trillion times too small to be measured or to be experimentally measured by the energies that we have available in the colliders today. So it's very difficult to actually zoom in and give the pictures I was drawing. So therefore, we don't have the luxury of using experiments to guide us in building our theory. So, and in particular, as I said, we have no experimental evidence of string theory to date. However, it turns out that even the incomplete knowledge of string theory gives us a lot of new principles of physics. It revolutionizes a lot of things we know about physics, even though we are far from the complete theory. And my aim is to try to give some sense of these new principles by guiding through some examples. So it's going to be, of course, difficult to describe all the things we have learned in string theory in one talk, but I will try to at least take you through the tour of some highlights of some of the important ones that we have learned. And so this picture is just to illustrate that I'm going to be talking about the parts under the lamppost clearly. I'm not going to talk about far away in the dark, which we still don't know. But even what I'm going to tell you, even under the lamppost, there's a huge amount we have learned, and that's what I want to convey. But before I even start with string theory, I want to step back and talk about some historical lessons we have learned through the history of physics itself. And in particular, I want to emphasize the fact that the development of physics and the new idea of physics comes always by giving up something we thought was fundamental and absolutely correct, something which we did not suspect can be false. This has happened again and again in physics, and as I will illustrate, string theory continues that tradition in that we have to give up a number of principles that we thought are sacred. For example, let's go back and remind ourselves that at some point Earth was viewed as the center of the universe. Now, in fact, the Greeks were very, very smart in recognizing, first of all, the fact that Earth was round, it's a globe, and they viewed, nevertheless, that the Earth is at the center of the universe. Okay? They didn't question that fact. Why not? It should be at the center of the universe. It looks, they didn't probably have this picture, but anyhow, they had the picture of some kind of a globe. And in fact, not only they had this idea that Earth is the center of the universe, they used it to argue why Earth is not moving. They thought Earth is not moving. So they wanted to explain why the Earth was stationary. And they had a very clever idea. They said, look, this is at the center of the universe. And if it were to move in any direction, it would break the fact that it's symmetric right at the center. So if it goes that way, you say, oh, no, it's not center anymore. You have lost the center, so it's not going to move. That was the argument for the Greek, that the center, the universe, that not only we are at the center, but we are stationary. So they used the symmetry principle to argue why we are not going to be moving. The Earth is stationary. Now, of course, we recognize that this is a false statement because we know Earth is moving and so on. But what I wanted to point out here is the clever use of symmetry argument they used to try to convey a physical fact that they thought was true. But actually, they were really smart. In fact, Aristotle disagreed with this reasoning. And in fact, he said, yes, of course, Earth is at the center, but this does not necessarily mean that because of symmetry it cannot go anywhere, because symmetry can be broken spontaneously. And he illustrated this by a very simple idea. He said, well, suppose you have a circle, and you have somebody at the center of the circle, symmetric like Earth or whatever, and you distribute food equally along that circle. Now, he said, are you going to tell me that the guy is not going to move to the circle to get food after a while and is going to starve to death? Okay, so he was saying that symmetry is not enough to say that preferred position is at the center. You will break symmetry to gain food in this example. You go some direction, and therefore you break the symmetry. So at any rate, the idea here illustrates that the combination of the symmetries, symmetry breaking, and so on was already being discussed by the Greek all the way back then. But nevertheless, they thought Earth was at the center of the universe. Today, we know that's one of the principles. That's not true. We have given up that long ago by now. There are other notions like this. For example, the absolute notion of time. There's time clicks everywhere the same way, we thought. And of course, this gentleman showed us we are wrong. Einstein showed that time is relative. We don't have an absolute notion of time. And it depends on which observer is measuring it. So the absolute notion of time also we gave up. How about the absolute notion of the state of a system? Now, what do I mean by a state of a system? Well, where things are. I mean, you say there's a particle there, there's this, that. Can you actually describe where things are in an absolute way? In other words, does it make sense to say where things are? And in fact, quantum fuzziness, the fact that if you try to describe the state of electrons in an atom, they look fuzzy. You cannot say exactly where they are when they have a given energy. They're kind of spread out. It says the absolute state of a system is also a little bit fuzzy. It's not quite possible to describe it that precisely. There's some fuzziness. So even that, we had to give up. So these sounded at the time, before these amazing revolutions in physics, sounded obviously correct. Earth was at the center of the universe. There was an absolute notion of time. And of course, you could say where everything is. And all of these by now have fallen down. These are not principles of physics anymore. Similarly, string theory calls for radical changes of our understanding of the fundamentals of physics. And as I said, even though we don't know the full theory, we know enough to know that this has to come about, and we have to have very different new ideas in physics. It is in some way reminiscent of early days of quantum mechanics, when they had discovered that things are wavy, but they hadn't quite written down the correct, precise equations that later was described by Heisenberg and Schrödinger. So we are in that stage in the development of string theory. We have understood that things are wavy, but we don't have a precise formulation of how that works. So this was of the way of a basic introduction to where we are heading. But I have to do the setting of the stage of what it is that, what kind of elements come into these new principles. And the most important thing that we have learned in string theory is duality. Almost everything we know, everything interesting we know in string theory is in some way captured by this concept of duality. What that means is the general statement that two very different looking things can nevertheless be the same thing. Okay, two things which look completely different can be manifestations of the same thing. This is the general meaning I want to use as duality, that two things are the same despite the appearances. So here, I have drawn a picture here that you should imagine like every point here describes a physical theory. So you pick a point in this, and every point you pick in this space corresponds to a solution in physics of some shape or something describing the physical theory. So you think about a particular point as fixing your theory. In that point, for example, the electrons have this and that property, and our universe looks this and that way, and so forth. That corresponds to a point. So it's a summary of the details of the physical theory is this point. But you can have different kinds of physical theories. This point can move around in this space. So this is the parameter space in which you can choose different kinds of physical theories. You can change the mass of the electron. You can add more particles, and this and that. So this is kind of motion in this space is changing the theory. And it turns out that there are some special corners in these theories where the physics looks very, very special. These corner theories, 1, 2, 3, 4, 5, 6 in this case, I've denoted, describe physical systems in which description simplifies. So you have an easy description. In the middle, the description of physics is very complicated. But in these corner theories, things will become very simple. So these corner theories, these easy theories that we can access, where we can actually describe the theory, are analogous to reference frames in Einstein's theory, which are useful reference frames. So as you may recall, in the context of Einstein's theory, physics might look different depending on how fast you are moving. So physics can be described relative to a particular reference frame. These corner theories should be viewed as particularly preferred reference frame that the description is easier. For example, if I'm in this room, the easier description is for me to stand here and describe the objects around me. Of course, I could make a funny motion, go around in loops and so on, and describe the physics that I would see that way. Of course, that would not be very convenient. So similarly, these kind of corner theories are useful descriptions of the same system, but it's easier to describe it. So you could think about them that there are these easier versions of this theory that are somewhat analogous to reference frames for which this physics description simplifies.